Thank you. Okay, so let us get going. Good evening, everyone, and special welcome, maybe I should say re-welcome to today's speaker, Professor Frank Hartmann. Why I said re-welcome? Because, of course, he's been part of the ICFA 2023 school. And then, so I would like first to thank ICFA school and especially its director, Professor Govinda Majumdar, for making this colloquium possible. And he's going to, of course, speak on development of silicon detectors in high energy physics experiments after those wonderful and very, very informative lectures that he gave to the students of the school. And I think he promised to kind of give a summary or overview of the entire developments that are going to take place. Without taking more of his time, but before that, I have this pleasant responsibility to request Professor Shashi Duggad to formally introduce today's speaker, and also I request him to conduct the rest of the proceedings. Thank you very much.
Thanks, I hope I'm audible. In fact, it's my pleasure to introduce Professor Frank, and we in the CMS community know him for a very, very long period of time because he's very closely associated with many of the upgrade activities that we carry out for the CMS experiment, in particular the phase 2 upgrade activities. And actually, you know, whenever he comes to India, he takes opportunity to visit several groups who are working on this program. So he's coming from Niger, Bhubaneswar, wherein, the tracker upgrade activity is going to be carried out. So Professor Frank, he got his diploma in 1996. And if I look at his career, it has been all in all on the silicon detectors. And he got his diploma on the Delphi microvertex detector from KIT. And then he joined the PhD program subsequent to that. And within the few days of his studentship, I mean, there was a discussion in his group to participate in the CDF experiment, more so in taking responsibility of making the tracker detector. And by then, I think Frank was already known within the KIT, I mean, his own group. And as a student, he was given the responsibility to go and kind of negotiate this program with the CDF with a kind of a minimal financial commitment, particularly on the entry fee and all those things. And he managed that responsibility quite well. And after they came, I mean, the KIT group was responsible for making the tracker for the CDF2. And so this was part of his PhD work as well, which he got in 2000. And later on, I think this is a kind of a prestigious degree after the PhD. It's a formal degree. It's called Habitillation, and which he got in 2018, which kind of clearly identifies Professor Frank as a person who can take a not only leadership role in a particular area. I mean, this is one of the recognition as part of this degree. And so he was ICFA R&D Roadmap and the TF8 Integration Chair in 2022. And as far as the CMS is concerned, I mean, as I mentioned that his entire career had been focused around the silicon detectors. So he was a project manager for the CMS tracker since 2011. And now I think his responsibility has further grown up. And now he's upgrade coordinator for all the phase 2 upgrade program, which includes EduCal, which includes Tracker, the GEM, and many, many other subsystems. So he's not only responsible for making sure that all the projects are going as per the timeline, but also to ensure the funding profile, particularly now he's going through a challenging period in view of the Ukraine crisis. But so this had been very big responsibility that he's taking since 2018. And with all these major responsibility, I don't know how, but he finds time. I mean, he has written a wonderful book on evolution of silicon synthesis technology in particle physics. And normally you write a book and yes, it is there. But right now that book is in its third edition. So certainly the book is quite popular. And I think it will be a very nice book for the student community and even for the faculties, who has interest in the silicon detector technology. And with that, may I invite Professor Frank to deliver his colloquium on development of silicon detectors for the high energy physics experiment. And I just want to tell you, even Professor Ravindra Kumar is here. They also make use of such detector to find out, I think, what is the acceleration and what is the kind of multiplication that happens, because their beams are highly focused. So if they want to know the number of particles, they use detectors of this kind. Maybe he can correct me if I'm wrong. Yeah, thank you.
Thank you, Shashi, for this very nice introduction. Thank you for the invitation. I'm honored to be here to speak. The current speaker said that it's good that I found time. This is an ICFA school for students. Whenever I manage, I always will find time for students. They are the future of our field. They're incredibly important. That's basically, after the CMS upgrade, my next highest priority. I talk about development of silicon detectors. I'm working in this field since 25 years, and we established quite a number of detectors. I have been asked to go a bit more technical than what I normally do when I go for students lecture. So with the sake of time on some items, I then went technical, I removed it a bit, but I will go there. And wherever you have a question, there are quite a lot of hidden slides. We can then, after I finish, go back and we can go in much more detail than what I'm going to show. So this is here what you see is that CMS tracker. This is the face of one of the NCAPs. These are my Austrian and Aachen colleagues. These are our Italian colleagues. So this is when we literally built the current CMS detector as its current shape. Now, let's see. No, yeah. No, it's fine. I just had to click once, was fine. Anyhow, so we're using silicon since the 50s, at that time really for energy measurements. Then afterwards, we needed a fast and precise timing position measurement. And here, silicon is just pristine. We have detectors that the whole signal can be captured in below 10 nanoseconds. I mean, today, 1-2 nanoseconds with a higher voltage is not a problem. We have precise position resolution. We kind of claim 5 micrometer, but it can go below. It can be sub-micrometer. So 1 micrometer, 0.5 has been achieved with strip sensors, and it has a very good energy resolution, about the factor 10 compared to gas detectors. Now, in the 80s, it has been used for charm tagging, and then in the late 80s for the lab experiment in the Vertex tracker. And after I introduced a lot of sensors, I will briefly fly through the systems also what we had in the 90s and the Hadron machines at Fermilab, and then today in all of the LHC experiment. And then in the backup, I also have the slides for the future tracker, which I didn't include here today. Now, the question is then, if this is also great, I mean, sounds great, numbers are great, then is the question, why wasn't it really used earlier? And it hasn't been used earlier because we needed really industry to do that. We needed a lithomicroscopy technology, and that was cost. At the initial times, it was just simply not affordable. CMS in 1999 decided to go, instead of 60 square meters of silicon plus 100 square meters of gas, to 200, but only because the cost of the silicon went down. By the way, the physicists working on silicon at that time vetoed the full silicon tracker because they said 200 meters is not doable. We proved them wrong correctly. In the today in all the, so in the end, the other problem is in gas detectors, you have amplification factor 1,000, factor 1 million. So that's fine, but in silicon, you do not have that. I mean, I show some sensors later which has amplification, but that's really more lately. Normally they don't have it, so we need microelectronics in the correct dimension that can then improve and increase the signal, so amplify the signal, and we didn't have that. We needed so readout electronics and miniaturization, and I will show you that the first detector in high energy physics had a factor 1 to 300 of sensor to electronic size, and I have a picture of that. Now, we are using them everywhere. We're using silicon most of the time, but also some of us using germanium, tellurium, and also diamonds. Diamonds are supposed to be more radiation hard. That's why we use really at the different beam spectroscopy, the time of flight, they're incredibly fast as well, GSI and LHC. Yes?
The slides are not moving on the Zoom somehow. Can you please try once?
I can unshare and reshare. I'll do that. And I hide again this one. So now this will go away. So we see we have silicon strips here at LHC, in Atlas detector, in LSCB, in ALICE, in CMS, everywhere. By the way, the second largest silicon detector that mankind ever built is not in Atlas, it's in the Fermi satellite. So the second largest silicon detector is literally flying in a satellite here at Fermi, which was initially called GLASS. Then here our nuclear physics guys, they use more germanium, where they can really do with Compton scattering, gamma tracking, and then the silicon pixels are really used at every LHC experiment, GSI in Darmstadt, in the ISS, in satellite experiment. And then also this is the new timing detector, which will come 30 picosecond time resolution in Atlas and CMS. And then the silicon photomultipliers here, you see them in all the dark matter experiments and also in the astroparticle parts, and here also in the calorimeters. 3D silicon is something I come later. This is the most radiation hard that we have so far. They will now be used in Atlas, CMS, and also for some timing detectors. They can be really ultimately fast. They can be, even if in the right thing, I have a 10 picoseconds time resolution. And then here, the CMOS sensors that I come later to there right now in the STAR experiment, in the ALICE experiment, and quite a lot of satellite experiment, and quite a lot of medical application. So from the historical point of view, here, this is the timeline from 1960 to 2040. This is a logarithmic scale on the surface, and you clearly see a first strip. I show that. Then the first one in HAP, NA11, and then it just goes up, and you kind of see the Moore plot here. At the moment, we're kind of saturating at 200 square meters, because otherwise it again gets too expensive, because if you go further than 200 square meters, it's quite a big deal. And the 200 square meters is just literally what fits into the current CMS and Atlas detector, so we would need to go further out. But some people put calorimeters there. What can I do? Now, still, now the HCCs or the HCAL, the forward calorimeter detector for CMS will have 600 square meters, so it's yet 3 times more. It's larger than Atlas and CMS together. And then the calorimeter detector for the future linear collider, they even plan 1,000 when 2 detectors, even 2,000 square meters plus on silicon surface area. So you can play a bit of football there, no problem. Huh? And that's what you see here. So that's a bit in the future. The pixel detector here, all the red ones, they're still ramping up like crazy. So here the smallest one was a several square centimeter, and now Atlas targets 13 square meters, and ALICE already equipped 10 square meters of these devices. And the cell size goes significantly down. In the CMS tracker, we are going from 10 million channels now to 220 million channels, and from 120 million channels in the pixel to 2.5 gigapixels. And ALICE already have 12.5 billion pixels in their detector. So quite impressive, the evolution here. Now, this is now, I've been asked technical, so I want that whatever we go later, you understand it. So I have 2 prerequisites, which I hope you will have the full stamina to go through, because they're technical. I want to explain 3 different things. Number 0, first, we have segmented diodes, which we do in reverse mode. I very quickly run through one slide how that is, but mainly I want to tell you that all the doping profiles in the PN junctions that you should find in every of my systems, and then the voltage applied for the reverse voltage, they kind of define the electrical fields. And then with the center geometry and the weighting field, that strongly defines the signal formation. And the signal formation is somehow really driven by the electric fields, which define the speed, the velocity, and then kind of the nearness to the electronics, or the capacitive coupling is the good thing. So kind of this is the path that we need when we design a detector. And then number 3, which for the LHC detectors, but also for any future detector, they need to be radiation tolerant. And I will come to some recipes, but only 4 slides, while normally if I talk about radiation, I talk about 2 hours if you really want to go into superficial details. You need more than 2 hours to get it there. So here I go technical. So let's start first. This is in a nutshell, number 0, how they work. Here we have an N-type detector, and here we have P-type. doping strips. So these go all the way through. They can be 5 centimeter, 10 centimeter, up to 20 centimeter if you gain the things long. Then here a particle comes, späte Bloch, you have an ionization. You then see here are the holes slowly drifting here. As soon as they're in the vicinity here, they then by induction give the signal. And you also see the signal, as soon as they are there, the signal stops. And the signal starts as soon as the particle hits, all goes by induction, and the faster electrons, they go down here. And here's the electrical field with the voltage. That's kind of how they work. And then dependent if they're here or here or here, this gives our spatial resolution. And in fact, if the particle goes through here, so let's say like this, then if this is the higher signal and then that one, then the real position can be done by interpolation of a center of charge calculation. So in principle, it's quite easy if you go into details a bit more. Now here I go now in this PN junction. So sorry, I once back. So this is the P, this is the N. And then basically here, since you put additional acceptors here, so holes, these holes travel here, the electrons there travel here, then they basically form this depletion zone, which is then space charge, because you do not have any free charge carriers anymore. That is kind of the volume where we work in. And that kind of then also defines the field. And I come to that. So if you now have an acceptor donation, so a doping of this part of the detector of acceptors and here of donors, then you have this part in between, where then you have the space charge density here, because all the extra electrons went here and the holes went there. And you already see that the one which has a higher doping concentration can penetrate further because it just has more excess of free charge carriers. So this is then the space charge density. Now, if I go a bit more formal, then I say, okay, you have no free charge carrier, that's fine. And then I do just the Poisson equation. So I take here the space charge density here in the Poisson equation. And then just if I integrate it once, I get the electric field. And this is what you have. Now, since this part here normally is only 1 micrometer, and that is 300 or 500 or 200 or 150, whatever, basically you only have the configuration of a linear field inside. If you go further, you integrate once more, you go squared. So you have a squared potential, and then here the diffusion here before the voltage then compensates the movement or basically stops the movement, then this depletion zone goes in the order of a square, so the diffusion voltage is a square of the widths that you have here. And that kind of also is the voltage you need. Now, what I want to take home here is that really the doping concentration here defines the field. So there's a direct correlation from here to here, and that is one of the main considerations we need when we deploy when we design the sensors. And then the external voltage keeps this thing out even further. And as soon as it's fully depleted, so the whole bulk is depleted, I have the right voltage. So that's the two things. Now, the next thing is, I said, many people are saying, you collect the charged particle that goes here on this electrode. But that's not exactly true, because as soon as the particles arrive at the electrodes, the signal is over. The real part, as in gas detectors, works via induction. Now, I have seen textbook which says it's mainly by induction, or I've even said one, in contrast to gas detectors, silicon gets the signal by collection. These textbooks are all wrong. Silicon detectors as gas detectors get the full signal by induction. So the drift is recorded, the height of the signal is proportional to the velocity, which again is proportional to the field. And then you have a weighting field, which somehow convolutes this one. And this weighting field can be difficult. And you can really tune your detector to have that, use that weighting field to your advantage. And we're going to do that. So if you would now have something where the weighting field is 1, then you fear your detector with the high field here, the low field here. So now you see the hole, they go in the direction of the high ones. So you see the current of the holes, if you would inject it in the middle, goes higher, higher, higher. So the signal goes higher because it goes into the direction of the higher field. So it accelerates, and therefore the signal gets stronger. And the electrons, which is intrinsically 3 times faster, gets into the lower field. So at a certain moment, it's even slower than the holes, and the signal is finally the integral of both of it. And if you do that correctly, then you can really tune your detector, but you always need to see velocity times field times the weighting field. Velocity proportional to the electric field, which is driven by the voltage, and the weighting field is what you get. And the real difference is that in gas detector, the field is constant, and in a silicon, the field is linear. That's kind of the difference, and the linearity and the height of the field, and therefore the speed, you define by your doping and by your voltages. Now, with the weighting field in the next slide, I show you, before then I really go to the meat, that with the weighting field, I can define if I kind of get my signals from electrons or from holes or from both. And later on, I show you why I want to get it from electrons, because I have trapping. Now, the signal formation here, all this I already said, but we often say we collect holes or we collect electrons because in a strip, you see, when the electron travels here, it kind of doesn't really see the electrode. Huh? But as soon as the hole goes in here, then it starts to see the electrode, and then it couples here with capacitive couplings much more. So the signal from the hole is highly emphasized. That in principle, in a strip detector, 85% of the signal we get is from holes, or if we change it from electrons. And in pixels, even worse, is even more. 95 to 98% only gets the signal from one charge. This is because of the weighting field, and you can really think about it like the collection electrode, the capacitively coupling. The further you're away, the less you couple, the less signal you get. And in addition, also normally the electric field is here highest, so you have a double whammy. You have a high field, a high velocity, and the nearness to the weighting field. So that gives you a good signal, and that's how we really do that. Now, in the future CMS high granularity calorimeter, which is a pad detector, this is not 85% or 98%. This is basically 50 to 50. I come to that. So here you register really electrons and holes, and that's one of the tricks why it works, because it gets double the signal. In the future high luminosity tracker, we register mainly electrons, and otherwise today we basically get holes, and this is a design choice, and I'll come to that why. Now, the last prerequisite before I go to the detectors is now radiation damage in silicon. I will give you a very, very brief glimpse. I should put another very, because as I said, I need normally 2 hours. But no matter what I do later, whenever I talk about the fluence, I always talk in equivalent fluence, which is always scaled down with a scaling law, which has been experimentally proven and measured to 1 MeV neutron equivalent. So then I can compare. Before that, we were just talking of different languages. So diamonds are still telling me only proton fluence with high GeV, which is damaging much, much less than, for example, protons at 5 MeV. But they're always comparing 24 GeV protons to our 1 MeV, which is completely unfair. Now, what these guys do, so here you see now a simulation from Michael Huhtinen at the time in CMS. You see a 10 MeV protons, they damage the crystal lattice, comes on the next slide. And here you basically see the distribution of vacancies. I could do the same simulations for interstitials, but basically vacancies doing the trick. You see you have basically uniform distribution of vacancies, or the same of interstitials. While if you go for higher ones, they do not create so many interstitials, small ones. They really have cluster effects, and the neutrons, which only react via the strong force, they basically make clusters. That unfortunately is not the end of the story. That fortunately is not the end of the story, because if you go from here to here, like a random walk, which is then diffusion, migration, breakup, and recombination, you see that here have quite a lot of recombination. So quite a lot of these atoms that just been replaced from the lattice, they just step back in the lattice. And so they cure themselves with higher temperature, the better. So that's good. But on the other hand, you have these nasty double, triple vacancies, which are bad, which give us additional energy levels in the band gap. And you see these are more prone for neutrons than for protons. Still, we can fully scale from here to here and vice versa. So we have a formula for that, which has been experimentally measured, but I don't show it today. Now, the examples of the crystal defects, we just simulated the vacancies, but you have the interstitials or the Frankel pairs. And of course, these are short reaching, so these in the annealing, they basically recover. The divacancies are not so easy to recover. Then you might have an impurity substitute. You might have an interstitial impurity. You might even have a couple of carbon and oxygen together, or you have an interstitial impurities. You see, you have a lot of different possibilities how you can disturb your lattice. And your lattice, if you go for solid state physics, where I have no clue about, then you know that all these different parts in a lattice form energy levels in the band gap. That means I now go away from my initial doping concentration, which I just really put bore in or phosphorus in, clearly exactly the amount I want. Now this changes everything. And if this changes everything, I have now three different things. I have leakage current, which is important from 10 to the 13 onwards. And these basically are creating these mid-level donors, these mid-level energy gaps. And then instead of needing to hop 1.1 EV, I only need to hop 0.6 EV. So you see, this is the perfect chain to increase your current. That's the reason why we need to cool down our detectors, because with radiation, they increase the leakage current. And with an exponential law, every 7 degrees, I can halve it. So 14 degrees is better. I can bring it down by factor 4 and so on. Now, these ones are even for the LHC even worse. So if you have another part here, and this is explicitly what we see mostly, the acceptor, you have another level which is close to the valence band. It's another acceptor. And that then really changes my doping concentration, my effective doping concentration. And 3 slides earlier, I told you that the doping concentration defines my field. And my field defines my signal, and it defines my operation voltage. So this is quite important. The next thing is even that comes from 10 to the 15. You have some things which are even more intermediate. They trap electrons or holes. They like it there. They keep them for milliseconds. Our integration time is 20 nanoseconds, 50 nanoseconds, or microseconds, but they stay longer, so these do not participate to the signaling anymore. So all that is bad. We don't want that. Now, this one I will not go in all the details, but in principle, you start with an N-type silicon, so N-doped. Then you add acceptors, acceptors, acceptors. They neutralize each other until you're intrinsic. And then you basically add only acceptors, and that's what we call type inversion when you go from an N-type detector to a P-type detector. Also the field inverts, also the depletion zone starts from the other option. And then wherever here you have this annealing, which then changes the property even more. I don't explain that. For the increase of leakage current, it just goes linearly up with a logarithmic scale. So just you add radiation, you just increase these interstitials, and they basically increase the leakage current. Leakage current, as we saw before, you saw this nice thing that they basically recover. They all the way go back down. With some engineering, we can then even do and say, okay, this is, so I now represent, I go for this curve. So if I go with the standard one, I'm ending up here. If I put carbon in, that's even worse because it blocks some of it forms some worse conglomerates of chemicals. And if I put oxygen in, the oxygens are binding quite a lot of the divacancies, we believe, might also be the vacancies, the single ones. And with this, it doesn't go so steep. And that is here the forward depletion voltage that I need to apply. And at a certain moment, I cannot apply the voltages anymore. So oxygen is good. Carbon is bad, and CMS and Atlas introduced literally for the current detector already oxygen to improve the radiation tolerance. Last slide on radiation damage is trapping. Trapping here, I plot the inverse trapping time, so going up is bad. Here you see the fluence basically goes linearly up. The annealing effect is plus minus 10%, so that's small that I can neglect. But if I'm at 10 to the 15, my trapping time is about 2 nanoseconds. The maximum saturated speed in silicon is 10 to the 7 centimeter per second. That means I can only travel 200 micrometer far. So if my detector is 500 micrometers thick, don't care, I can only get the signal out of 200 micrometer. And as you saw before, I want to have it near my electrode. So all the stuff that I have in the lower side doesn't really contribute. If I go to 10 to the 16, my travel distance is 20 micrometer. So I really need to start thinking. That's difficult. I show you in the last slide that for the FCC-HH, we want to go to 10 to the 18. We have no clue yet how to do that. Now, I now give you the recipes. The content of impurities is important because it defines the forward depletion and therefore the field. The depletion, the operation voltage goes linearly in the field. They create donors. We also like to create donors, not only acceptors, and their oxygen is literally creating donors. That's why it's so good. It's creating also donors, which then compensate for the acceptors and you stay longer in N-type. We even have some materials where we can choose from P-type to N-type, where we overcreate donors. So this defect engineering is quite nice. So you already see I have more green points. You need high field to get the signal. So if now you do a thinner sensor, then this helps because you need less voltage to deplete it for the same fields. And it goes with the thickness squared. So you really gain if you go thinner. And that's why in the future, high Lumi pixel detector, we go to 150 micrometer only instead of the standard 300. It also reduces the path length, that's the trapping. So you really use much more of the volume because of the 20 micrometer than with the 300. And then the next thing is you use N in N or N in P sensor, then you have an N electrode. And an N electrode is a donor one, so it sheds away all the electrons, meaning the remaining space charge is positive, electrons out, remaining part is positive. So it registers electrons because it attracts the electrons. Electrons are 3 times faster than holes. So they're less prone to be trapped. They also travel further. The electric field and the weighting field is higher at the N electrode. I cannot really go there, but after the type inversion in P, you would have still the large electric field at the electrode. You always have the high field at the electrode. At N readout, you have the high field at the electrode, but the weighting field, you always have the good weighting field at the electrode, but in the P and N readout after type inversion, you have the high field on the wrong side. So this acceleration on the wrong side. If you use an N readout, then after irradiation, you have the weighting field and the electric field at the right side. So you overcompensate, you convolute that. So this is why these are the things: thin electron readout with an N electrode, and you add some oxygen to also use this part. So this part is always at the electrode, but in an N type, also the high field is afterwards here. In a P type, the main junction here is later after type inversion in this side. So the highest field is here, but you want to have it here. Prerequisite stopped, and I'm a bit out of time, but only by a couple of minutes. So strip and pixel sensors, which are the workhorses for LHC. That's fine. Strip and pixel sensors are the workhorse for the LHC. So this is the most simple detector. This you can just put in the lab. You can measure photons. You can measure muons from cosmic rays, everything. So here you see that I have about 1 micrometer deep diffused into the bulk material, my doped P type. This is then in the order of 10 to the 15, 10 to the 17 doped. This is 10 to the 12. If then I put 100 volts, then I can fully deplete that, and the depletion zone starts to grow from here to here until it really reaches the end. The guard rings here are for field shaping, and they also somehow compensate for the edge here, which is cut with a diamond saw, so it's rough. A rough crystal lattice always has damages. Damages as, again, energy levels. So it's the main enemy for leakage current. And then here from the technical side, I have another N plus dope. So an N doped, highly N doped, which is quite conductive, just to avoid the Schottky contact from the N-type silicon, which is low resistivity, so high resistivity to a lower resistivity, to avoid here a Schottky contact, to improve the ohmic contact. Normally, we always have a hole here that we can shoot a laser in for calibration purpose, but that's kind of the picture. So if now I take this and I segment it, so now I take, for example, an N-type detector here and I make a P, 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 P. So this is exactly what I had before, but now I have it segmented. And then when the particle comes through here, then I can see where it is. And this is kind of this part, the weighting field of these strips is 80 to 90% of only one charge carrier. So in the P and N, the holes go here, the electrons go there, 300 micrometer thick with an electric field. This is what we have in the current Atlas and CMS detector. At the time, we didn't get pure enough P-type. So now you see here also the numbers, and we operate today up to 600 volts. If now you want to reverse that, you basically reverse all the colors. So you make the N to P, you make the P here to N. You have a one-dimensional readout still. The resolution can be down to 1 micrometer if you wish. 4 micrometers is what we kind of use, and most of the time we use 20 or so. Here you do the depletion voltage. So again, that's fully depleted. And here you have the electrons moving up here instead of the holes. So again, faster. And then we normally also go a bit thinner. Now, you need, in addition, these so-called P-stops, because you have one more problem here, that now the oxide is normally positively charged. The N-doped part, again, shedding the electrons, is positively charged, so it attracts electrons. So all this here attracts electrons. So I have an electron accumulation layer. I would short circuit the strips. That's why I need to put in an P-stop in between who repels the electrons and therefore guarantees the strip isolation. There are more things like that that I'm coming to, but this is the main normal use case that we're doing. This is then the real life detector. So here, this is really CMS. You have this edge field shaper for the cut edge. Then you have the guard ring, which I showed you also the diode. And here you have a ring all around, where you replace the ground potential. On the back, you place the high potential. And then you have these poly resistors, which reaches the DC pads. And then the DC pads via via is connected really to the electrode. And the aluminum strips here, they are above a silicon dioxide. So a decoupling capacitor that the electric current, so the leakage current is basically running through the implant, through that, but they don't reach the amplifier. The amplifier are capacitively decoupled. That was the first time we used that in Delphi. Before that, everything was directly, all currents was directly flowing into the ASIC. So you had to put big capacitors in ASICs. It was difficult. So that was the first time in Delphi when we really implemented the coupling capacitor in the sensor. That was a huge step at the time. So the implementation here, since this is then 10 centimeter long and only 100 to 200 micrometer thick, you can have up to 600 picofarads of coupling capacitance. If you want to put that in the chip, at that time, that was really difficult. So at the time, sometimes build pitch adapters or something with additional capacitance to decouple and make sure that the leakage current is not destroying the ASIC. This is a PNN, so this is a CMS detector. And now again, as I said, I just basically put everything, I invert all the colors, and then I just additional these P-stops to make sure that the strip isolation is here. And you really see they run all around. These are so-called atoll P-stops. You can also combine them, then they're common P-stops. But this one is better because if one fails, only that strip fails. If you have a common one, if you have any defect somewhere, the whole detector fails. So that's the most common solution that also our main supplier is doing. And we already get more than 100 square meters of detector for the current future CMS detector, and all sensors are excellent. You can also do double-sided, and whoever worked in Bell, somebody who worked in Bell too, you know, I'm jealous because when we did double-sided detectors for CDF, afterwards Hamamatsu said, we will never ever produce double-sided detectors anymore. They're too complicated, the yield is too low. And then the Japanese came and said, I have a Japanese experiment. And then they built double-sided detectors again. Now, this is a Delphi detector. So here you basically see here again the bias strips. You see here the strips and the implants. Now here you have the implants. And then up here you have another interesting thing because all the readout is on that side. So here you basically then have another silicon dioxide and you have a double metal here. So this is metallized. And then with these vias, you can route all the strips which really go into this direction. So orthogonal to that direction, you can route them out that you can read out everything on one single side. But that is really the state of the art. That's basically the most complicated you can do. And they also thought about the isolation, but they do not have P-stops. They increased the metal a bit higher and put it under negative potential to repel the electrons with a so-called field metal plate. That's a second option that you can do. If now you go to the Bell detector, again, I'm quite angry that they're only building things for you. They again are here put the P-stops in as we had before in the N in N side, because here you have P in N and then here you have N in N. So you need, again, isolation. The next thing would be a pixel detector, which is real 2-dimension. And if you know where it's in space, you have a real 3D dimension. But here you really need to connect every single cell to every cell in the readout. So you have 100% coverage of readout ASICs to the sensor. And actually, the cost of the sensor plus the cost of the readout ASIC is smaller than the cost for the connection process. So that's the main cost in these devices. And you have a lot of channels and you have a lot of readout channels. That means you have a lot of connections and you have a large power consumption. So you really only do pixels where you really need pixels. Otherwise, you don't. You see here, this is the underbump metal. So I show another picture of an electron microscope of these bumps here. So basically here you have the sensor where you have exactly all the P and N junction here. You have the beta part, the electron goes here, the holes go there because this is an N in N. And then you connect it here to the readout with a specific ASIC. You have a 2-dimensional readout, can be superb up to small numbers of micrometers as resolution. And the weighting field really makes sure that you just get one part of the charge. And that's why here it shows already for CMS only electron readout. Side remark, for phase 2 CMS will have 30 square meters of that, because even a large part of the outer tracker, 25 meters of the outer tracker will be pixelated with 1.5 millimeter pixels. Here's the picture of the thing. So here you have the pad where it goes to. This is the photolithography where you put basically the bumps. You warm them up to balls. Then you have the sensors. These balls are most of the time on the chips. And today you can buy in the company where you buy the ASIC, you can buy also the balls already on the grid array. Sometimes you have to go to another packaging company, and then you go to the third one, who then basically flips chips it and puts it together, which we often also, that's the last part we often do in-house. Then you have something very familiar for my colleagues here at TFR. Then you have the silicon pad detector, which for the colorimeter. So here you have really these hexagonal sensors here, one first time that we use an 8-inch sensor. And my standard question is, why do we use hexagonal sensors? And the answer is cost. Because you make much more use of the real estate of that sensor than if you would here put the rectangular one in. So this is really, you save 30% of the cost by doing that. You have other problems later, but still, the other problems are not overweighing that, because you tile an end cap, that's fine. And then you tile the end cap in the following way. You go with 100 micrometer thick sensors in the middle, and 200 micrometer, 300 micrometer, according to the radiation field. So you have a much higher radiation field here, and that's why you go thinner. And you have a lower radiation field outside, that's why you go thicker. And then here, basically, you put a PCB on top of that. And I just heard IQ at Bangalore can now really do this complex PCB, because here you have this incredibly complicated stepping here that the PCB is up there, but here you have another connection that the wire bonding works for every single pad individually. And these are also NNP, which are more radiation tolerant, and then you go with the thickness as you need. And the good thing here is that the weighting field, you really collect or you register both charge carriers. It's incredibly good for the colorimeter, the resolution. It's not sufficient for the tracker. But again, for me, that's the blueprint. You also have seen that the future linear colliders are targeting CALICE to have such a detector. Okay. Now I go for other silicon detectors. This is kind of the future. So 3D is what we will use in high Lumi, LHC, CMS, and Atlas. Atlas is already using it. Then we go for the low gain avalanche detectors, which I will convince you that we have a 30 picosecond timing. And then we briefly go through monolithic active pixels, and there, depending on the time, I will go into more or less details. For all of these, I do not have time, but if you want to have any information of that after the last discussion and question rounds, we can go back to the slides. They're in the talk. So let's go for 3Ds. I was bitching about all the time, sorry about my language, that you want to have short distances because of trapping. So as soon as you go 10 to the 16, 20 micrometer is kind of the goal. But if I make this thing 20 micrometer thick, first it's close to not thick, the signal then also is so low that with my standard electronics with a threshold of 1000 electrons, I cannot do it. So going that thick doesn't work. And then in addition, if I go here down, then the capacitive of my cells would explode. That means my noise explodes. So I have a small signal and I have a high noise. So it doesn't kind of work. So 150 micrometer here for the passive sensors is the sweet spot. It kind of works, but then you need the voltage, which goes squared with the thickness. So you need in the order of 800 to 1000 volts, which gives you a lot of power, which you need to take out by cooling, which is mass. And you don't like any mass because of multiple scattering in a tracker. Now, with that argument, I now say, okay, now I go for 3D sensors. So now instead of putting my plates just on top, I really basically make a full column through the detector. So here you see one of these columns, and they work with deep ionizing etching. So what you do, you basically, instead of just etching and then basically have such a pyramid form in here, you basically etch, then you passivate, you etch further. So this is not etched anymore. You passivate, you etch, you passivate, you etch, you passivate, you etch. And with this, they were able to drill in the order of 200-300 micrometer thin down. But then since these should now only be in the order of 4 micrometer, 5 micrometer wide, kind of now the sweet spot is 150 micrometer. And here you see microscopic electromagnetic electron microscope pictures of the cut edge of these 3 detectors. And with that, you have the full volume, so you have the full signal, but you only have the travel distance here, and you only need the voltage from here to here. So the voltage is subdued by 50 over, let's say, 300 squared. So you only need 100 volts instead of 800 volts. So the power goes down dramatically. They need much less power and a much more radiation tolerant for trapping. They have a higher capacitance, but not so high that we're really afraid of it. We can use it with the same chip that we use for the other ones. And also now, since now you can anyhow etch down, you can now also etch away the edge. And then etching is a much more smoother process. It disturbs the lattice much less than a diamond saw. So now you can also gain up to 0.5 micrometer of otherwise inactive edge at the area. So you can tile this detector much better. I hope I'm technically enough. Now, this is what we really finally use. So here you have a picture. And that was after many, many iterations. You see here, you have columns only from the top. You have here from the top and from the bottom. There's a double-sided process. And basically now we go only from one side, but these things we do not go all the way through. These we get all the way through. This is now low ohmic, so it's basically conductive. So with this, I can bring all these to the same potential. And these ones are now individual, and I connect them with bump bonding as a pixel. There's a proper pixel detector to the readout system. So I have a full detector with here. This is now in the order of 30 micrometer distance only. Remember, 10 to the 6, 20 micrometer, 30 micrometer here, perfect fit, 150 meter active thickness instead of 20 or 30. The only problem is it's very difficult to produce them. The yield is not fantastic, but we only need 0.5 square meter. So that's just doable. And then they work after 10 to the 16. And that measurement is already 3 years old. We can even go higher to that. And they give, again, the two-dimensional readout with a superb resolutions, and the granularity is also very superb. It's close to this one. This is not the latest one. This is just one before. It's a bit thinner. Was the first trial. But I think it's very nice to see that here you have the first an oxygen barrier here, and then you have you fill it with polysilicon, which is before the polysilicon goes in. The polysilicon is doped, and that's how you then can have a P or an N column. And then here you have basically an N column here with the doping of the polysilicon, and this one is polysilicon doped all the way through. There is no oxide around it. This you really etch fully through. And then here, at a certain moment, you have this low ohmic wafers. This is still a box, so a buried oxide, but they made the possible direct wafer to wafer bonding, so direct silicon to silicon bonding. So that just works. Now, second but last of the species, this is what you have in your mobile camera. Here you now go with a standard CMOS process in some of the companies. You only have 1 to 20 micrometer epi layer with a P handle substrate. So this is kind of this does not have a high resistivity. Then you have here your full NMOS electronics. Unfortunately, only NMOS because you only have the N in the P wells. The N well here is just the collection electrode. And you have no bias voltage. That means your depletion zone only depends on the difference in the doping level of this one in here. And since this is heavily doped, your depletion voltage is very shallow. It's out of the 15 micrometer, maybe 3 micrometer. That means every particle that you have here needs to kind of randomly walk here, but of course some randomly walk there, some randomly walk in the other direction, so only some arrive. It only works because the capacitance, therefore the noise here is in the order of 10 femtofarad, so it's very, very, no, it's even below 10 femtofarad. So the noise is in the order of 10 electrodes here, but it's slow. This is in the order of 100 nanoseconds process. So it doesn't work for CMS or Atlas, but Alice is building basically 10 square meters out of that with some bias, and I show it. The two-dimensional resolution is absolutely superb. So 2, 3, 4 micrometer resolution is feasible here. That's what you have in your camera. If you now go a step further, so now I do not go to the standard fabs, but I go to some from the automotive and explicitly the power industry, which know how, with what they can work. So one more problem is, even if you can put a voltage here, then I want 100 volts here, and these work with 2.5 volts, I would immediately burn the electronics. So what I really need to do is I need to nest now my PMOS and NMOS cells, or if I double nest it, I can have a full NMOS and PMOS cells in a deep well. So I'm protecting that. So now I can put the full depletion voltage here, and I then collect here the electrons, or if I have a small diode part here. This one is faster because the drift is quicker, but the noise is in the order of 100 electrons, while the one on here says in the order of 10 electrons. It's therefore a bit slower. And we're using that, as you see, we use that in many parts. The main trick is you need a backside voltage, and the real part is you have a voltage, so you have a drift and not a random walk. That's really the main part here. If you then go a bit step further for this part here, you have then this depleted zone. This has in the order of 3 volts. You still see it's a lateral depletion. So, but this part here is not depleted. Here you still have random walk. If now you make another contact here, you make another dose implant, then now you can deplete the full thing, because you do not deplete only from here, but you deplete from the full plane. And then you also have now all the target goes here and then basically go there. This is still not the best thing to go there and there, or here and here, or here like this, because this is still not the perfect way. The perfect way would be straight. So now you make another, and I'm not going into detail, but now you can also factorize that. So you don't do a doping here, or you do another deep doping here. So you kind of stepwise lead the electron really to the electrode. And this is here in the order of 10 to the 13 resistive, and you need about 30 nanoseconds. This now goes for 1 nanosecond is radiation tolerance to 10 to the 15. So this is really wherever you need a radiation environment item that is not just the LHC, then this is what you do. The ALICE built that. So the first one with the 3 volts, 10 square meters, 12 billion pixels. They thinned them down to 50 micrometer, and they have 30 by 30 micrometer pixels, and basically no material in there. The next upgrade for LS3, so 2026-89, they want to now replace the inner layers with something that is even thinner, with a pixel of 10 by 10, with a 3 micrometer resolution, X naught of even a factor 10 better. And now these things are curved. And they have the curved ones in the test beam, and they work. So they put the full electronic, full monolithic, no wire, no bump bonding, no nothing. And I put it in the beam, curved, and it works. It's not radiation hard enough for our inner layers in Atlas and CMS. It's not fast enough, but for ALICE, incredibly good. Now, the one thing somebody asked me this morning, of course, if you want to do that, you want to have big detectors, but the reticles on CMOS fabrications are normally 26 by 32 millimeters only. So you cannot really build a 10 by 10 centimeter detector, but you want a 10 by 10 centimeter detector. So what you do is you go yet another smaller number of companies who can do reticle stitching. So instead of doing a reticle of 25 by 30 millimeter, they go something by 1 centimeter. So they now form these blocks. And then with these blocks, what they have here, they can basically form the inner one. This is the pixel region. This is this one here. And then, for example, the 1A, this is this part here. And then they just put these reticles together. And whenever they come here, you see this one is the reticle of this part is exactly the same here. So you oversample and you overdo the photolithography in all the stitching lines. And the current plan of ALICE, which has not yet been proven, is they want really to go to 200 micrometers, so 8-inch wafer, and do a full stitching of this amount of sensors, and have done a 25, so this is 300 micrometer, a 25 by 14 by this size, a full detector, which then they can bend. It's not yet proven, but they have all the ingredients to do that. One more slide there, and then I just run over detectors, but I felt that here I want to go more into the details of really the systems. So here now I have the same thing. I have basically an N and P detector, but here I do another thing. I now put another P layer here. These are both highly doped. The doping concentrations are defining the field. So here I have a high field. So now I have the standard mechanism. Hole travels down, electrons travels to the N electrode. But then here it reaches a field which is higher than 2 times 10 to the 5 volt per centimeter. That means here I have a real electron avalanche. This is like in a gas detector. Now this brings me to a signal with a gain of 20 to 30, where then the signal is so steep that in the steep, the signal itself has a small jitter. And the jitter here, so the deviation from the perfect line up, gives me a timing resolution. And what I can do here is 30 picosecond time resolution. This detector has 2 flaws. It has a bad fill factor because the time resolution only works in this area, but not in the middle. So they have a dead area of about 20% of the detector. These pads are normally in the order of 1 millimeter. So the spatial resolution is not so great. That's what we will put in Atlas and CMS, but I call it obsolete. We can do better. So next step is, instead of doing these p-stops here and having these 50 micrometer gaps, we now do these trenches, the same thing that we do in silicon photomultipliers, 3D etching, just 1 micrometer deep. And then I can go from 50 micrometer to 1 micrometer dead zone. So my fill factor is then more like 98% instead of 80%, but my spatial resolution is still quite bad. These are called trench isolation LGATs. Here you can also add a carbon layer, gain layer in here. That kind of avoids the, now initially I said carbon is bad, but in here, whoever wants to know, carbon is good. That's the only place where carbon is good. After we reinvented the LGATs, and we were quite proud that we invented that, we realized that some people were already more clever than us. They invented it in 1972. But literally, we only realized it after we invented it. So, you know, communication over generations is not so easy. The next step, and then I'm done with detectors, is an AC LGAT. So now here I basically have, instead of these islands of amplification areas, I have a full amplification area which spans the whole thing. I do a silicon dioxide, the same thing that I do with standard strip detectors to isolate it. And then I can pattern the things here in, let's say, 150 micrometer pitch. And since this layer is now conductive with the conductivity that I can control by the doping concentration, now we need machine learning, we realized. But then I have a timing that is 30 picoseconds, as good as the LGAT. I have a fill factor of 100%. Do you see any dead zones? No. And if I can do this ratio here correctly, then with 150 micrometer pitch, I get an incredibly experimentally proven 5 micrometer resolution. That's the future. And the EIC, so the Electron Ion Collider in the US, is already planning 11 square meter of time of flight with that. It's not yet proven, but it's already there in their concept. I love that. I think this is really the future for everything we need. And it's radiation tolerance 10 to the 15. So unless we really go in the innermost detectors, that's it. Unless you are FCC HH, where they need even further. For the systems, I have my probably 5 to 10 minutes because we started a bit late. I run through, and I was planning to run through. Here, this is the first strip detector in 1971, and the Institute for Experimentelle Kernphysik of the University of Karlsruhe and the Kernforschungszentrum of Karlsruhe. And I'm just pointing that out. I'm exactly in that institute, although it has another name, and I'm also at the campus of the Kernforschungszentrum, which is now embedded in the KIT. And also here, I only realized that after 20 years of work or 15 years of working with these detectors. They basically have 12 gold strips. That was not a position detector. That was just an energy measurement. But depending how the particle penetrates, of course, you have a longer path. So you can correct if you know the angle where it comes from. So that was done there. Then you have this Na11 detector, which is basically built on 2-inch. So is literally, this is the sensor. And then you have no electronics, no ASIC electronics here. You basically route all of them out to the standard NIM crates or whatever we had, 1970 something. And then we have 8 of these silicon sensors behind. That was a big success. We were able to take charm quarks with that and measure their lifetime. And the position of these guys were 4.5 micrometer. So literally excellent. These were really the pioneers. I completely skipped Delphi, but here is now the collider detector at Tevatron. This is the first 10 square meter detector ever built. That was my PhD thesis. This is the first time that we use 6-inch wafers. Today we use H. Industry is using 12-inch. So we are kind of stuck in the 90s. We're still in the order of 30 years behind of what industry is doing here. We all say it's top-notch, state-of-the-art. Funding agencies don't listen. But in principle, we're there. But with the CMOS, we are now touching the 12-inch. This is the first time that silicon was used as a state alone, and these are radiation tolerance to 10 to the 30. Then people, and the story here is whenever we built that, every sane physicist said, don't do that. It will never work. In a hadron environment, hadron on hadron is so messy, a silicon detector doesn't work. All cells will be lit all the time. They will just fire all the time. The unsane physicists were happily right. This allowed the top quark discovery of CDF. Without that, no top quark discovery because no tagging of the B quark. As John Ellis told us in 1980, if we cannot do that, we will not win. Then we went even closer. So then we started to put the detectors directly on the beam pipe. And here the CDF people at Tevatron, they went to the LHC CMS guys and say, you have mastered the 10 to the 14 radiation tolerance. Can you give us your detectors? And we did. So these are now detectors from the remaining detectors that we had as spares from the first trials. This is basically real scrap material. And these are now going 10 to the 14 and the outermost is 10 to the 13. The CMS silicon strip here, this is the 200 micrometer, the 200 square meter beast with 3 layers plus 2 pixel detectors. And then depending if you're stereo angle to get a 2-dimensional one, 500 meter thick, 300 meter thick. Again, you see we're adapting the thickness on the needs and on the occupancy, and we target a percent-wise occupancy. And down here, we want to have an occupancy of 10 to the minus 4. That's here why we need to go to pixel 100 times 150. In the future, we go 25 by 100, meaning a factor 6 down. Nice pictures of this forward pixel detector. Big puzzle for grown-ups. One of the reasons I do that, because I love puzzles. As long as they're like this, the ones on the table I don't, but this is really fun because you can measure if you're right. You don't, and without pattern recognition. But this is then how we insert the 3 layers barrel detector. Here of all the cooling pipes, and we can insert it while the beam pipe already is in place. This is then the full barrel installed, and then we do the pixel. And we can do this full maneuver of installing the pixel detector in one day, meaning we can extract in a technical year and technical stop. We can in principle extract and reinsert the pixel detector in a year and technical stop. This is then the CMS detector. This is again this nice end cap. We have 9 of these discs. This plus this makes the 200 square meter. Hell of work. This I like quite a lot. This is the pre-shower detector in front of the forward calorimeter. And quite a lot of the strips here, I think 30% have been of the silicon strip detectors themselves have been produced in India, in Bangalore. I think the company is SEL or SEL? SEL. Well, I'm sorry, I'm BEL. Okay, so this is in front of the calorimeter and they're working. So really good. Then we have here another piece of art, the Bell 2 vertex detector with here the different layer in the middle, a pixel detector, again, standard pixel detector. Then outside you go for strips. This is the double strip detector. Again, I am really angry that we didn't get double strips. And this has been delivered also by TFR and company. So that also shows a strong expertise. And you had built these things in Japan, mainly largely built in Japan and also in Vienna. Quite a lot of my colleagues, dear colleagues, worked on that. This is then the real next thing, the HCAL, where silicon enters the calorimeter on the large scale. The first current imaging detector is about that size. Here we want to equip more than 600 square meters on 8-inch wafers that I've shown already earlier. Here you have the electromagnetic part, the hadronic part. And then here where the radiation zone is not so strong, we use plastic scintillators, so silicon photomultipliers on tile, also 400,400 square meters. So this whole detector here is 500 square meters and then another 500 square meters of stuff on the other side. And here you see one of these countries, which I hear will be delivered next week. So you will just miss it unless you go to customs. So this will be at TFR in a week's, thanks to the directorate who supported that. And then here you have this huge sampling layers, 26 sampling layers of electromagnetic calorimeter and 21 sampling here. And we hopefully build a good fraction of that here at TFR. So already big thanks for all the effort you're doing. The future then, the real big beast is then the FCC-HH. That's my last slide. It's the reference detector here. And you see here, we go beyond the 1 meter in diameter. We go almost to 1.5 and we go all the way 16 meters down here with silicon sensors. 1.6 meter, half length, 16 meter with a 4 Tesla solenoid in the B field. They will run with not a pileup of 200 at Weevil, but they will run up to a pileup of 1,000. And that means they are aiming for a 5 picosecond time resolution per cell. We have already prototypes that they can do 2 picoseconds, 3 picoseconds, but they're not radiation tolerant. We have one detector that can do 10 picoseconds or even less better, which is radiation tolerant and has the right position resolution of 10 micrometer. but that's again a 3D detector that we cannot build in that size, but maybe the inner layers we can. And then they have to withstand 10 to the 18 1 MeV neutron equivalent. Remember how to do that? Good, because I haven't told you, because I have no clue. And I don't know expert in the world who knows. Thank you for your attention. And I end up with these nice things of, this is an interesting picture that we did. This is the Megadeth who found also it's an interesting picture. They put it on their CD cover. Of course, they didn't ask us. And then if anybody's a fan of Star Wars, if you zoom in here, I'm pretty much sure that they just put this picture inside. I'm up for questions.
Yeah, thank you. Thank you for a nice talk and actually giving a very nice tour of the development of this silicon detector since last several decades. And now the colloquium is open for questions. So are there any questions? Yeah. Go ahead.
Yeah. So while speaking to student, like when you talk of this, you saw that proton, pion, and the neutron, sort of how they impact the silicon. So the question is, why don't we say in terms of proton equivalent or pion equivalent or the neutron equivalent in terms of, is that because it is the bare minimum impact it carries?
No, it's not the bare minimum.
What's the underlying?
It's simply kind of more easy to understand because we also use quite of reactors where we basically have in the order of 1 MeV neutrons, which is kind of one of the main sources. For the protons, then we like to go too high. As soon as you're then at 800 MeV or a GeV, then your proton damage is almost the same as your neutron damage. If you go down to, let's say, 20 MeV, what we, for example, have in the Karlsruhe irradiation facilities, then your radiation damage factor is a factor 1.8. If you go to Birmingham, it's a factor 1.6. So you're there in the order of 30–40% effect, 10% effect. You need to calculate it. It's just something that they sort 1 MeV neutrons to sounds nice. We could also have said 1 MeV protons, but you kind of, neutrons is kind of here standard of a radiation that also nobody of us can avoid, because you always have a gas of neutrons flying, thermal neutrons, which are in that order through your detector. But you also, I mean, if you go into more details, then, and if you go to different materials, again, I need 2 hours to explain your radiation. But if you do magnetic Czochralski or oxygenated magnetic Czochralski, or if you do epimaterial, the radiation in all of these things depends on energy, on the type. And this clear scaling really only works for trapping, and it works for leakage current. It doesn't really work for the acceptors and the donors. As you've seen, as soon as I put oxygen in, already there I basically broken the Neal violation. Is a standard, then we all know what we are talking about. And we could have used 3.8 MeV pions, but we normally don't have many pion sources. So we have a lot of neutron and proton sources.
Yes, Doc.
I come from a low energy background. So how does this compare with, let's say, 5 MeV alphas, which is standard stuff, let's say for 30 or 100 micron silicon detector?
So
it is 1,000-fold improvement in some of the radiation damage things.
I mean, there's also a factor to alphas. I mean, they damage a bit. I mean, we do also from time to time heavy ion radiations. So whatever we get in any of the sources, we do some alpha calibrations. I mean, the detector, of course, is perfect for alphas, but then normally you do not take the aluminium. You take the aluminium away. You use just the doping with a higher doping, and use the silicon as a conductive area to bring the voltage to the PN junction. And then it's a perfect alpha part. In fact, it's even better because your signal, of course, with the Bethe Bloch goes squared with the charge. So it's a perfect detector for that. For the radiation damage, 5 MeV is not them. Let me think. I don't have these numbers in my head. You start photons from 1 MeV. 5 MeV. No, it's probably factor in the order of a factor 2 to the 1 MeV proton equivalent. Maybe a bit more because of the double charge. But you know, the double charge, no, I don't think, because the double charge, then you lose the energy quite quickly in the ionization. And the damage only goes in the non-ionization loss. So when you really kick off an atom. So now it's about the same. But I had to think a bit. We're not using alphas so often. So for the detection, wonderful. For the damage, I'm not really afraid of alpha particles. And also they don't penetrate far.
You mentioned about the time resolution of less than.
A bit louder, please.
Yeah. So you
Now it's on, but
so you mentioned about time resolution of less than 30 picosecond in some of these detector. Yeah. But
LGAT, the low amplifying avalanche detectors.
But what is the lowest you can get? Because in the last slides you mentioned about 5 picosecond or so.
So that's do I have chalk? I have chalk. I found chalk.
Yeah.
So the point is, it's not really the, I mean, you can get the signal, can still take the 3 nanoseconds. You don't care. You care on the steep rise. So the steep rise basically goes like this, and the time resolution is in the jitter of this. Okay. So now the time resolution in these LGATs is solely limited by the so-called Landau noise or the Landau spatial fluctuation. So you understand when you have a Landau curve, the thinner you go, when you have a detector which is about that thick, okay, then you don't know if the charge is created here, lots here, then nothing, then a bit here, and then a bit more here, and then maybe something here. This is the spatial distribution. It could also be that everything is done here, nothing here, and then only something here, you know? And all of this basically creates yet another peak line here. And that creates you then even a bit more jitter. Now, then you need to understand which detector you have. If you have an LGAT basically has the cell here, the amplification is here, so the real-time measurement starts at arrival. If you have now one which works with the induction principle, so you only have, instead of this double pad, you have a single pad, then it works immediately with the induction, with the weighting field. Then it's even worse, because, you know, here is the 10%, here's the 30%, here's the 70%, and then it even is important where you are. So now that means that is the ultimate killer for the timing resolution. That's why in an LGAT we cannot really go below 30. Now we can go below 30 if now we make the detector only 30 micrometer thin or 5 micrometer thin, because then the fluctuation gives me less of these curves. I have less signal, but since I amplify it, it's still okay. So that's kind of the thing. So if you go thinner, it's fine, but then there's a limit. So now the ultimate one that people are thinking is, but that's very complicated to build, because you need really several wafer bonding, growing another wafer that you basically make an unpart here. Then you make in the order of 3 micrometer away, you make another, here you make the gain layer. So here you make an N here and a P here. And then you make even a monolithic ASIC ones with some pads here, which can really then be with a nested one in the order of only 20 micrometers. So you have a perfect spatial resolution. You now only have in here, there are floating things, but you don't care. The amplification layer is only here in 3 micrometer. If you go there, then you can go down with a concept of 1 to 2 picoseconds. They have already proven with the first detector, I think in the order of 5 or 7. I don't recall the numbers exactly. And then all this cloud that you have here in the amplification in one cloud moves up here. So with this, you beat the Landau noise or the Landau spatial fluctuation. The only problem is you need to put this wafer, then, which is very thin, then you have a handle wafer, then you dope it, then you dope the next step. And then you need to come with another wafer, which is 30 micrometer thick, and you need to bump wafers on wafers. And then you need the full CMOS lithography process here. And then the remaining thing is not the sensor, it's the electronics. That doesn't work with CMOS process. Then you need to go to silicon germanium to have the speed. But if you do that, then you can go to 1-2 picoseconds timing resolution in the silicon detector. This is a so-called monolith process. It's an ERC grant done by the University of Geneva. That's kind of the state of the art. But that's, again, so intensive to build that I personally, as a detector builder, don't see how we build tens of square meters out of that. But the concept is wonderful. But the timing, the real limit is that you have a lot of these things independent if you go for drift time or for waiting field. The 3D sensors, they basically go and have now, instead of these columns, they have really literally plates. They have basically plates like this. Now, in between these plates, so again, you now have a full thickness where the particles come through. But now the particles can go in this and in this direction, but the waiting field is constant again. So you don't have the jitter from the waiting field here. You have a very homogeneous waiting field. You don't care if the thing is produced here or here, because every moving particle counts from every space the same, because it goes on both sides. But again, here you have now again a 3D process, which is not a pillar, but it's a wall. And the next problem that you have, then you build a wall, a wall, a wall, a wall, a wall, and then basically you have a flat silicon with trenches. And you know what the thing does? It does like this. We're all overcoming these problems, but in the timing regime, the field is lively like hell. We have so many good ideas there, is wonderful.
Thank you.
I hope that answered your question.
Hello.
Yeah, there's
Oh.
one question from YouTube, which I
Okay,
will ask
please
first.
go ahead.
This is, I hope you can hear me.
Yes.
This is Abhinav Chaudhary. He asks, is silicon drift detector? I know it didn't touch much, but is silicon drift detector suitable for detection of energetic electrons?
Sure. Sure. Nah, that's not what I wanted. I wanted the there again. Let me.
Yeah. Yes.
Okay, right? I mean, because YouTube audience.
No. Where's my silicon drift detector? Here is my silicon drift detector. Yes, of course, you can detect electrons with that. I mean, electron is a charged particle. Electron works according to Bethe Bloch, does ionization. Electrons does here the ionization. And then the drift detector is kind of working that you have here P plus and P plus. So you basically have no active field here. You have a lateral field, so your depletion zone goes from there. And then you kind of put the things to the right potential that they basically have here a slope that they go to the edge, and then you have a three-dimensional readout, because you basically measure the drift time in silicon, which is fast, and you have it. So you have here the one-dimensional readout, and then with the drift you have a two-dimensional readout. But this is a silicon detector which detects any charged particle.
Yeah, of course, this is.
So it's two-dimensional readout. The resolution is okay. The granularity is okay. I know people who work with it, and they say the calibration of that is no fun. So that's why I'm not working it, because I want fun.
Yeah.
Can
if
I,
I can.
can I?
Oh,
Oh,
yeah. Yeah, if I
I'll
can
ask at that.
ask one question. This is related to more of engineering, integration of detectors with the front-end electronics. Now that we talk more and more of silicon going all the way from tracker to calorimeter and beyond. So how is the front-end work, especially in connection with integration with the detectors, is progressing?
Oh, that's a very general question. I mean, we just recently went through this ECFA, so this European Future Collider process where we defined the R&D. And I personally was one of the two chairs to chair the integration aspects of all the detectors, for neutrinos, for dark matter, for collider detectors. And there's a lot to do. Now, if you, for example, ask me the integration aspects for CMS for the future, there we are now probably 90% with all the engineering done. But there is a question, is a hadron a calorimeter? In the calorimeter, you have a completely different part. You don't care about mass. You just care about empty space that you want to have because you want to contain the shower. You need to have the cells in the right way. Still, if you use silicon, you need to cool it. In the tracker, you want to have no mass, so you don't really want cooling lines. We sometimes cool with gas cooling, most of the time today with CO2. So the engineering aspects are incredibly important, and every physicist who says anything against an engineer is not allowed to come near me, because I personally think we have too many physicists at CMS or at CERN and not enough engineers. I personally applaud any engineer because we physicists, we have some good ideas, but we are just too stupid to do them. I mean, come on, we would be nothing without the engineers. And honestly, the engineers would have much less fun without us. I didn't really answer your question, but it's so broad that
I will catch you up.
yeah, you can do, but you can
just if I can take 10 seconds.
Yeah, if you take me to a specific engineering challenge, I'm sure I can answer.
No. I was really meaning on-chip integration with detectors and the front end, because
Okay.
detector and electronics
Okay.
is anyway is silicon, and I meant co-located integration of front
Okay.
end with this.
So that part is clearly solved. We have basically all the sensor technology for the high Lumi in hand. We're still waiting for the final ASICs. The previous versions of the ASICs were already wonderful, but they had some tiny flaws that, then you're in a very high radiation, you have single event LED shops and single events, which would have occurred too often. We just found that in simulation. So there's still work ongoing on the final ASICs. So for the pixels, I'm not sure if it's out today or in the next days, then the real final version for Atlas should go out. The CMS comes 3-4 months later, because we still have to assemble the chips, but all the IP blocks, everything is there. So then you have the ASICs, we have the sensors, and we already prototyped a lot with the hybridization, so the connection. So we have now 2 to 3 partners in industry, others are Atlas even 4, because we need so many of them that the throughput is quite difficult. And of course, we don't get access to the bump bondings of, for example, IBM. In addition, IBM, they have the so-called C4 bonding, bump bonding, which is kind of 200 micrometer distance. We want to go to 25 or 50 micrometer. So we're basically going yet the next edge. And for the future, we would like to have pixels which are only, what is the current thinking? I think 10 by 30. Yeah. So then you need to go even. So the fine pitch bump bonding is still a challenge. But there we work quite heavily with industry. Also, the Fraunhofer Institute is our main industrial and most reliable partner here. But that part of the equation is solved. What we are still working on, that outside we have a DC-DC converter, which we fully master. Inside we need serial powering because we cannot bring enough cables inside to get the power. Because the future tracker has, I think, 150 kilowatts of power at minus 35 degrees in a 20 cube meter volume. With biphase CO2, monophase would not work. Now, challenges are there everywhere, and fortunately, we have good engineers.
Maybe I'll just ask one question. Yeah. Yes. So I just want to ask you, I mean, are we still using this ion implantation, or mostly it's done through the epitaxial growth? I mean,
No,
for example,
it's all ion implementation.
oh, these are all with the ion
Everything.
implantation.
Everything.
Oh, okay.
Everything.
Okay.
The only epitaxial where we grow the bulk is for the 120 micrometer HECAL sensors. Everything else is float zone. In some areas, we wanted magnetic Czochralski as a base material, which we didn't get. So we all use float zone material only for this part. So the epitaxial growths only go for the HECAL. And then also for this one, because here, of course, this 3 micrometer here is epitaxially growing. Because you cannot have you cannot cut the wafer. You need really to grow it.
Exactly.
But then these things here, all the patterns, all the strips, all the pixels is ion implantation. You
I see.
make a photolithographic mask and then you
But
bombard.
you can go as deep as you like, or these are very shallow.
No, you don't want to go as deep as you
Mhm,
want. You go in the order of a micrometer deep.
Oh, with that, for that, perhaps the ion implantation is okay. But
Yeah,
most
you
of the
can- you
needs
can-
are of
You
that
can go,
kind.
you can go, I think, in the order of 3, maybe up to, but we don't want that. So the standard recipe is 1 micrometer.
Okay, okay. Okay, I think we can discuss more during the tea. And thanks everybody. And we can.
Thank you again for the invitation.
Yeah.